After spending several days looking at exponents and what we can do with exponents and numerators and denominators, we're going to look at exponential growth functions. So we're going to look at writing functions. We're not going to look at graphing too much because we've done some of that already. Mainly writing equations, then calculating certain answers to questions with those equations. So the first thing we need to consider is what is an exponential growth function. So when something grows by the same percent in each time period. So the time period can vary from seconds to minutes to years. There's a lot of variations it could be, and that will often be a rate. So for instance 6%, or it'll double, but there's going to be some type of rate in the way it's going to grow. A distinguishing between two terms, we're not going to distinguish too much between them, but we have a growth rate, which is going to be your percent. How are you increasing? And then the growth factor, which is what you're actually going to use in the equation. With exponential growth and exponential decay, we're always going to kind of have a starting point at 1. With exponential growth, we're going to add to that. That's why it's 1 plus r. So a 6% will be 1 plus 6%, so 1.06. When we do exponential decay, we're going to start at 1 and go down. So if something decays at 6%, we're going to do 1 minus 6%, which would be 94%. So growth factor is kind of starting at 1, going up or down. The growth rate is actually just the percent. So we want to identify the initial amount and the growth rate in this exponential function. Exponential functions, remember, always a times b to the x. A is your initial amount, b is your growth factor. So 135, that's your initial amount. The 1.80 is our growth factor. But we're looking for the growth rate. So remember, the growth factor is 1 plus the rate. So the rate would just be 0.8. And if we convert that to a percent, that would be 80% as our growth rate. So the growth rate is going to be 80%. Next example, a rancher begins his herd with a longhorn cattle with 15. So that's going to be our initial amount, 15. And the herd grows by 30% per year. So that's your time period per year. 30% would be our growth rate. So we need to plug in our growth factor as growing, so we're going to add it to 1, and 30% changes to a decimal is 0.3, so 1.30 to the x, where x is the number of years. So 15 is your initial amount, 1.30 would be your growth factor. Example 3, we have now a savings certificate. We're putting some money in the bank. We're going to put $1,000 in, so that's our initial amount. And then it pays 6.5% interested compounded yearly. We're not going to worry so much about the compounded yearly. We'll focus on that some later time when we have other varying compounding. So here's our rate, our growth rate. So we need to add that to 1. So 1.065. Remember to change it to a decimal, move it 2 spots to the left to the x, where x is the number of years. So that's our equation. What's the balance when? The certificate matures in 5 years. So what we're going to do is take x and not use x anymore, but we're going to plug in 5, and then we're going to calculate that. So 1.065, we're going to raise that to the 5th power, and then times 1,000. So the answer we get is $1,370.09. $1,370.09. With the next example, we're putting $600 in an account that pays 4% interest compounded yearly. So y equals our initial amount, which is 600, and then it pays 4% interest, so the growth rate is 4%, so the growth factor would be 1.04 to the x. And again, with this case, the balance after 7 years, so x is going to be 7. We're going to plug 7 in, so 1.04 raised to the 7th power times 600. Remember from order of operations that your exponents are always evaluated first. That's why I've been saying and calculating the 1.04 to the 7th first, and then that times 600. So $789.56. With the first last three examples, we've had a percent given to us. With these next two, it's not going to be so much a percent, but it's going to tell us what happens. So here an experiment starts with 100 bacteria, so that's still going to be our initial amount. They double in number every hour. That actually gives us the growth factor is 2. They double in number every hour. So our time period is going to be hours, and it's doubling. And again, x is still the number of time periods. So find the number of bacteria after 8 hours. So we're going to plug in 8 here because x is the number of hours. So 2 to the 8th is 256 times 100 is 25,600. So they didn't give us the growth rate, they gave us the growth factor, which would be, if you can think of it as a rate, 1 plus, it would be 1, so it would be 100% growth rate. The final example, we have an initial population of 30 rabbits, and they triple every year for 6 years. So our initial amount is 30. And then the growth factor is tripling, so it would be 3. So it would be a 200% growth rate, 1 plus than the 2, to the x. They triple every year for 6 years. So we want to calculate when this is 6, what do we get? So 3 to the 6th is 729 times 30, 21,870. So if the rabbit population triples every year, you start with 30 rabbits, there would be 21,870 rabbits after 6 years.